Every day you send password, credit card number, and personal message across the internet, traveling throughout dozens of servers you don't own or control. So why isn't every hacker in the world intercepting all of it? The answer is encryption, especially three technologies working silently in the background: TLS, IPSec, and VPNs. By the end of this video, you will understand exactly what each one does, how it works, and why it matters even if you have never studied networking a day in your life. Part number one: the problem with encrypted data. In the early internet, data traveled in plain text, usernames, password, messages, completely readable to anyone who intercepted them along the way. This is called a man-in-the-middle attack, a third-party security that sits between you and your destinations, reading or even turning everything in transit. Encryption fixes this by scrambling your data so that intercepted traffic looks like random noise. Only the intended recipient with the right key can unscramble it. There are two core types of encryption you need to understand. Symmetric encryption uses one shared key to both lock and unlock data. It's fast, but it creates a chicken and egg problem. How do you securely share that key before you have a secure connection? Asymmetric encryption solves this with two linked keys: a public key you share with everyone and a private key you hold. Anything encrypted with your public key can be only decrypted with your private key. This makes it possible to send secrets to someone without ever agreeing on a key before it. In practice, the two work together. Asymmetric encryption is used once at the start to securely agree on a shared symmetric key. Then, that faster symmetric key handles all the actual data. This is the heart of how TLS works. Part number 2: TLS, Transport Layer Security. TLS is a protocol securing the vast majority of internet traffic today. It's the reason URLs start with HTTPS instead of HTTP, and it's why you see a padlock icon in your browser. Banking, emails, shopping, social media, it all runs on TLS. TLS evolved from an older protocol called SSL. In the early 1990s, SSL had serious vulnerabilities and was eventually replaced. Today we use TLS 1.2 and TLS 1.3, with versions 1.3 being the current standard, faster and more secure than its predecessors. You will still hear people say SSL casually, but technically all modern secure connections use TLS. TLS provides three guarantees. 1. Confidentiality. Your data is encrypted so no eavesdropper can read it. 2. Integrity. If anyone modifies your data in transit, TLS detects it immediately and kills the connection. 3. Authentication. TLS confirms you are actually talking to who you think you are, not an impersonator. That third guarantee, authentication, is handled by digital certificates. Certificates and certificate authorities. A digital certificate is basically a verified ID card for a server. It contains the server's public key and domain name, and it's signed by a trusted third party called a certificate authority, or CA. Well-known CAs include DigiCert, GlobalSign, and the free nonprofit Let's Encrypt. Your browser comes preloaded with a list of CIS it trusts. When you visit a website, your browser checks whether that site's certificate was signed by a trusted CA. If yes, the connection processed. If not, you get the red "Your connection is not a private" warning page. The TLS handshake. Every time you open a secure website, a TLS handshake happens in a fraction of a second. Here is the short version. Your browser says hello and lists the TLS versions and algorithms it supports. The server responds with its certificate. Your browser verifies the certificate, then both sides use a mathematical process called Diffie-Hellman key exchange to agree on a shared session key without ever directly transmitting that key. Finally, both sides confirms everything worked and encrypted communication begins. TLS 1.3 streamlined this to a single round trip, cutting connection time and improving speed. One more important feature, TLS 1.3 requires something called perfect forward secrecy. This means a fresh unique session key is generated for every single connection and then discarded. Even if someone records your encrypted traffic today and later steals the server's private key, they still cannot decrypt your past sessions. The keys are simply gone. Part 3, IPSec, Internet Protocol Security. TLS secures specific app-to-app connections. IPsec works at a deeper level. The network layer and encrypted all traffic flowing between two network endpoints, regardless of which application sent it. Think of TLS as sealing a specific letter in a secure envelope. IPsec is building an encrypted tunnel between two cities, so everything passing between them is automatically protected. Two core protocols inside IPsec. AH, authentication header, verifies that packets are genuine and untempered, but it doesn't encrypt the data itself and it doesn't play well with NAT. The technology that lets multiple devices in your home share one public IP. For this reason, AH is rarely used alone. ESP, encapsulating security payload, is a workhorse. It provides encryption, authentication, and integrity all in one, and it's not compatible. Nearly all IPsec deployments use ESP. Two operating modes. 1. Transport mode encrypts only the data portion of a packet, leaving the IP addresses visible. It's lightweight and used for direct communication between two specific devices. 2. Tunnel mode encrypts the entire original packet, including its IP header, and wraps it inside a brand new packet. The source and destination are hidden. This is the mode used to build VPN tunnels. IKE, Internet Key Exchange. Before IPsec can protect traffic, the two endpoints need to agree on how they will communicate securely. That's the job of IKE, Internet Key Exchange. IKE works in two phases. Phase number 1 establishes a secure channel between the pairs. They authenticate each other and agree on key material. Phase number 2 uses that channel to negotiate the actual IPsec connection parameters, which algorithms to use, which key and for how long. IKE version 2, the current version, add an important feature for mobile devices. If your phone switches from a Wi-Fi to cellular mid-connection, IKE version 2 silently re-establishes the VPN tunnel so you never notice the disruption. IPsec is a backbone of enterprise networking, connecting branch offices, securing server-to-server communication, and powering corporate remote access systems. Part number 4, VPNs, Virtual Private Networks. A VPN creates an encrypted tunnel between your device and a remote server. Over the public internet, all your traffic travels throughout that tunnel, hidden from anyone on the outside. To the rest of the internet, it looks like your connection is coming from the VPN server, not from you. Types of VPNs. Remote Access VPN. A single user connects securely to a remote network, the typical work-from-home setup. An employee's laptop connects to the company's VPN, and they can access internal system just as they were sitting in the office. Side-to-side VPN. Two entire networks are connected together. A company with offices in New York and London maintain a persistent encrypted tunnel between both locations, so employees can access resources across sites seamlessly. Consumer VPN services. Services like NordVPN or Mullvad, you are not connected to a company network. You are routing your general internet traffic throughout the provider's server. Websites see the VPN server's IP, not yours. This hides your traffic from your ISP and can bypass geographic content restrictions. VPN protocols. Not all VPNs are built the same. The protocol underneath determines the speed, security, and compatibility. PPTP, one of the oldest. Avoid completely. It's been cryptographically broken and offers not real security. L2TP IPSec. L2TP creates a tunnel. IPSec adds encryption. Widely supported, reasonably secure, but can be slower and may struggle throughout some firewalls. IKE v version 2 IPSec. Fast, stable, and excellent for mobile devices, thanks to seamless network switching, a solid choice for both enterprise and consumer use. OpenVPN, open source, highly trusted, and very flexible. It uses TLS under the hood and can run on port 443, the same port as HTTPS, making it extremely difficult for firewalls or censorship system to block. Requires third-party software, but it deeply trusted by security professionals. WireGuard, the newest and fastest growing protocol. Its entire codebase is roughly 4,000 of lines, compared to hundreds of thousands for older protocols, making it simpler, easier to audit, and harder to exploit. It's faster than every competitive protocol, connects almost instantly, and is power efficient or mobile. WireGuard is now built into the Linux kernel and used by most major VPN services. It's quickly becoming the new standard. What VPNs actually protect and what they don't. A VPN protects your traffic from local snooping, hides your IP address from websites, and can bypass censorship. But a VPN doesn't make you anonymous. Website can still track you throughout cookies and browser fingerprinting. VPN won't save you from malware or phishing, and once traffic leaves the VPN servers, it travels normally across the internet. With a consumer VPN, you are also shifting your trust from your ISP to the VPN provider. Make sure you choose one with independent security audit and a verified no logging policy. Part number 5. How they fit together. TLS, IPsec, and VPNs aren't competitive technology, they are complementary layers. TLS works as the application layer, securing specific connection between apps, your browser, and a web server. Your email client and a mail server application must be built to use it. IPsec works as the network layer, automatically encrypting all traffic between two network points. Applications don't need to know it here. VPNs are built on top of these protocols using IPsec, OpenVPN, or WireGuard to create encrypted tunnels across public infrastructures. In real life, all three are often active at the same time. An employee connects via an IPsec VPN to reach the company's network. Then inside that network accesses a web app secured with TLS. Their data is encrypted twice simultaneously, once by TLS, once by IPsec. That's not redundancy, that's defense in depth. Every time you see that padlock icon, every time you connect to a word VPN, every time two office locations communicate securely, TLS, IPsec, and VPNs are working together in the background. TLS secures the web, authenticating servers and encrypting specific connections. IPsec secures the network, protecting all traffic at the IP level. VPNs create private tunnels, giving individuals and organizations encrypted passes across the public internet. Understanding these tools makes you better, smarter, more security-aware user of technology. If you found this useful, like the video and subscribe for more no-jargon deep dives into cybersecurity and networking. Leave a question in the comments. We read everything. Thanks a lot for watching. Stay curious, stay secure.